Our project is called Optimization of Multi-Axle Drive Systems Using AI, done in partnership with Wabtec. Modern freight locomotives use multiple traction motors to drive their axles. Today, when the engineer requests a certain power level, the controller usually just splits the power equally across all motors. That's simple, but it ignores the fact that motors age differently, cool differently, and don't have identical losses. The result is extra energy wasted as heat, higher fuel use, more emissions, and more stress on certain motors than necessary. Wabtec's question to us was, if the engineer's total power command stays the same, can we use AI to decide how power is split across all axles so the locomotive runs more efficiently? To explore that safely, we first built a MATLAB simulation model of a 6-motor locomotive. It captures key electrical and thermal behavior of the traction motors under a shared cooling system. You can think of it as simulated telemetry. We can feed in speed, power demand, and temperatures, try different power splitting strategies, and measure how much loss they create over time.
On top of the simulator, we tested 5 decision-making approaches. First, a physics-informed neural network, where a neural network is trained with the motor physics built into its objective, so it learns patterns that still obey basic electrical and thermal laws. Secondly, a small online learner plus a constrained optimizer, which regularly updates its estimates of each motor's lossiness, then solves a small optimization problem to choose the least loss power split while matching the engineer's total command. Third, a short horizon forecaster and planner, which looks a few seconds into the future to predict temperatures and losses, then chooses splits that are efficient and avoid drifting towards thermal limits. Fourth, a rule-based controller with calibrated maps, where we encode explicit engineering rules like favor cooler motors and tune lookup tables from simulation instead of learning from data. Fifth and finally, we had a shielded policy learning, where inspired by reinforcement learning, a learned policy proposes power splits and a shield enforces safety and feasibility before anything would reach the actual plant. Across all of these, one constraint never changed. The train always sees the total power the operator requested. We only change how that power is shared between motors. Running these controllers in simulation, we found that a non-uniform power split can reduce internal drivetrain losses compared with equal split. Among the 5 methods, the physics-informed neural network stood out. It consistently found lower loss allocations while still behaving in ways that made physical sense, which gave us more confidence than a purely black box learner. Some of the more aggressive learning methods looked strong numerically, but their gains often depended on fragile assumptions. The PIN offered a better balance of performance and trustworthiness. It's important to emphasize that these are simulation results, not yet field data. The MATLAB model is rich enough to compare strategies and see patterns, but real locomotives will add more noise in edge cases. So we view our results as directional. They show that the smarter power allocation has real potential, and they help Wabtec prioritize which AI approaches are worth carrying into hardware in the loop testing and eventually controlled trials on actual trains. In short, our work suggests that without changing hardware or how engineers drive, there is meaningful room to improve efficiency simply by making the power split across existing motors smarter, using AI that is tightly coupled to the underlying physics and safety constraints.